Hello, my name is Josephine Kau, ID 131182205. For the course MS3200 Basic Phenomenon in Mechanical Engineering, I chose to do an experiment based on Osborne Reynolds dye experiment. Basically, the experiment is to observe the types of flow in pipes and then to calculate the Reynolds number of the flows. From this experiment, there are three types of flows that can be observed. If you look at the picture on the right from the top, turbulent flow, transitional flow, and laminar flow. As seen from the figure, the flows are illustrated by the dye streaks along the flow. Osborne Reynolds was the first scientist to ever make a distinction between the types of flows in pipes. He also defined the dimensionless parameter that is widely used in fluid mechanics when dealing with flows in pipes. It is called the Reynolds number, named after him. The Reynolds number is the ratio between inertial force to viscous force. The equation can be written as such: ρ, the density of the fluid, times the average velocity of the flow, capital V, times the diameter of the pipe, capital D, divided by the dynamic viscosity of the fluid, mu. The equation can also be written as the average velocity V times the diameter D divided by the kinematic viscosity of the fluid, denoted by nu. The apparatus and setup of this experiment can be done at home and does not require complicated equipments. This was a sketch that I drew which depicts the setup of the experiment. The apparatuses were bought online at cheap prices. So here we have a ball valve of size half-inch diameter pipes, and a used bucket. The half-inch diameter pipes are sold at 50 centimeters long each due to expedition reasons. Thus, the pipes need to be joined together using connecting sockets. The bucket is a used bucket at home, and a hole was cut on the bucket side to fit in the pipe. The hole was made using cutter, but it is important for the hole to be cut not too big. To avoid possible leakage, the pipe is sealed with seal tape. Here is a view from the outside and the inside of the bucket with the hole. If you look at the picture on the right, you can see that there is an infusion pipe filled with food coloring. The end of the infusion set is a syringe from which the food coloring will exit. If you look at the picture on the left, there is the syringe right there. The joint between the syringe and the pipe is taped to the transparent type to ensure stationary syringe and dye output. This is how the whole setup looks like. The tall standing pipe on the right is used to hold the infusion set filled with food coloring. Now if you look at the bucket on the right, there is a stool below it. In order to set the pipe horizontal, a stool is used to prop up the reservoir bucket so that the other end of the pipe and the valve is at the same level. The procedure for this experiment is not complicated, and it will be explained in the following slides. Before starting the experiment, it is important to ensure that the ball valve at the end of the pipe is closed. This is done so that the horizontal pipe is fully filled with water. Now before the bucket is filled with water, ensure that there are no bubbles inside the pipe. Should there be any bubbles inside, slightly open the valve at the end to let some water out. If there are no more bubbles inside, close the valve and throw away the water from the container bucket. Now fill the reservoir bucket with water up to a level above the hole. As you can see from the video on the right, the hole is submerged. This is done so that the water can flow to the other side of the pipe. Then start the stopwatch and immediately open the valve. The valve serves as the control for the water flow rate. To have a laminar flow, open the valve slightly to let small flow rate. On the other hand, to have a turbulent flow, open the valve widely to let large flow rate. After the valve is opened and water starts to flow, Inject the food coloring into the flow. Previously, to prevent the food coloring to dilute into the water, stop the flow on the infusion set so that no food coloring can exit the syringe. Now, start the flow and let the food coloring flow with the water. Observe the phenomenon that occurs here. On the left, we can see a straight line of dye that exits the syringe. This can be categorized as a laminar flow. On the right, we can see a messy random flow, illustrated by the random messy dye streaks. This is called a turbulent flow. As the dye is injected, remember to record the phenomenon. After enough volume of colored water can be seen on the container bucket, or after the water level on the reservoir bucket is near the hole level such that the pipes cannot be filled fully, stop the stopwatch and close the valve to stop the flow. Now pour the colored water from the container bucket to a measuring jug. Be careful not to spill the water. Take a picture of the jug and read the volume of the water from the jug's scale. Another option is to weigh the water and the jug and then later convert it to volume using density. However, this is not done in this experiment. Repeat these steps for a few times. In this experiment, 3 trials were done for laminar flow and 3 trials were done for turbulent flow. Repeat as much as necessary. Finally, record the measurements taken into a table like shown. For the section, more detailed visualizations of the experimental procedure will be shown. Using the same procedures as the previous one, now we try to create a turbulent flow. After enough water is filled in the reservoir bucket, the valve is opened widely so that the flow rate is larger than the previous one. On the right, we can start to see the wavy and random paths of the dye streak. The dye streak is comparable to the previous one, the laminar flow. This flow is turbulent and chaotic, whereas the previous one is straight. At the end of each trial, the stopwatch is stopped, the valve is closed, and the colored water is transferred into a measuring jug. It is difficult to stop the stopwatch together with closing the valve without another helping hand. If you were to do it alone, do it one by one. Finally, measure the volume of the colored water. The values are then inputted into the tables as shown here. These are the data that can be obtained from the experiment, as well as data that are derived from the equipments used. One of the objectives of this experiment is to obtain the velocity of the flow. The continuity equation is applicable for this experiment, as the amount of water that flows into the pipe is equal to the amount of water exiting the pipe. Thus, applying the continuity equation, we can find the velocity of the flow by the equation volume divided by area times time. It is important to note the unit conversions. Using the velocities found from experiment and water properties found from data, we can calculate the Reynolds number of each trial. The Reynolds number can be calculated using the equation shown earlier in the video. As can be seen on the upper table for laminar flow, the Reynolds numbers are all less than 2,100. Thus, it can be concluded that the flows are laminar. From the bottom table, however, we can see that the value for trial 1 is between 2,100 and 4,000. This indicates transitional flow. As mentioned previously, it is difficult to distinguish transitional flow from turbulent flow using the naked eye. This can be distinguished using the Reynolds number, as what is done here. Thus, the first trial is a transitional flow, whereas the second and third trials show Reynolds numbers close to 4,100. It can be concluded that the second and third trials are turbulent flows. In this slide, we can see the video on the left showing laminar flow, whereas the video on the right shows turbulent flow. The distinction can clearly be seen between the two flows. However, for these two flows, it is difficult to distinguish using the naked eye. It can only be done after calculating the Reynolds number. The video on the left depicts transitional flow, whereas the video on the right depicts turbulent flow. It can be observed that for the transitional flow, the dye starts similar to a straight streak and then disperses. On the other hand, for the turbulent flow, the dye streak is totally random and messy from the start. This might be one method to distinguish the two flows. In conclusion, by replicating the dye experiment done by Osborne Reynolds in the 19th century, we can physically observe the phenomena of laminar, transitional, and turbulent flows, as well as calculate the Reynolds number. It is difficult to distinguish transitional flow from turbulent flow only through observation, but this is made possible by calculating the Reynolds number. We can compare the values calculated to the standard values and determine the types of flow. There are several possible improvements that can be done. Due to limitations of apparatus, the pipes need to be connected using a connecting socket. Although the connection of the pipes are sealed with seal tape, it is possible that there is leakage from the joint, as well as from the bucket hole. Also, the connection between the pipe and the bucket hole may cause minor loss. However, these are not put into the calculation. It is best to have a whole long pipe instead of several pipes connected by another accessory. Also, for each trial, it may be better to set one variable constant. For example, the time for each trial is set to be 5 minutes. Then the other variables adjust based on this set variable. All of these may affect the results of the experiment. This project is lacking in many ways, yet it has exposed me to a basic yet fundamental phenomenon in fluid mechanics. Thank you for your attention.